to the Crazy Hat Chemist, so another video here on Thermochemistry Part 2. So let's get moving. Bam! So today we are talking about an entropy change of a system, calculation number 1. So we're going to calculate the entropy change of the system for the reaction, giving the partial table of thermodynamic values at 25 degrees Celsius, which is 298.15 Kelvin. So here's the equation. It's 2 nitrogen monoxide gas plus oxygen gas yields 2 nitrogen dioxide gas. So that is the equation. It's a balanced chemical equation. And then here is a partial table of thermodynamic values here. Now I've included more values than what we need, but that way it enables you to look at what the reaction is and what the thermodynamic values are, and for you to pick out the values that you find necessary, that you deem necessary to solve this problem. I want you to notice that the entropy values are different than the enthalpy values for the units. So look at these entropy values. And they are in joules per Kelvin mole as opposed to the kilojoules per mole of the enthalpy values. So, something to note, because we're going to be working with enthalpy and entropy and eventually combining them together with Gibbs free energy later on. But take a look at this partial table that's in the blue. I have nitrogen monoxide, that's 210.76 joules per Kelvin mole. I got oxygen, molecular oxygen at 205.07. Oxygen, the atom, at 161.055. Ozone, that's O3, at 238.92. And then nitrogen dioxide at 240.04. I want you to notice that I've included 3 different ones for oxygen, and that is molecular oxygen, the oxygen atom, and ozone. And you need to pick the correct one, which of course is going to be molecular oxygen, and that's O2 in this example. I want you to also notice that there are no elements that are 0 at standard state conditions for entropy values. So for an entropy value, there will always be a value. They're positive values. They will always be a value for every single atom, element, molecule. No matter what, there's going to be a value. Unlike the enthalpy and Gibbs free energy that we'll talk about later on, where there are values that are 0 for the elements in their standard state. So, something to note. So, when we are calculating the entropy change for the system, we are doing the products minus reactants 1. Okay, that's products minus reactants. So delta S naught for the system is equal to the sum of the S naught for the products minus the sum of the S naught for the reactants. So what we're going to do is substitute this into this equation here. We're going to get delta S naught for the system is equal to moles of nitrogen dioxide. And then we got the units there of joules, Kelvin, moles. So joules in the numerator, Kelvin's moles in the denominator here. And we're multiplying by the moles, so then we will end up having joules per Kelvin. Again, very important, and it's very different than the kilojoules per mole units, or ending with the joule or kilojoules units. That's very important here with comparing the enthalpy and the entropy. Okay. I also want to take a look at that balanced equation there, and I want you to notice that we are starting with 2 different gases and we're ending with a single gas. Now we have 2 moles of nitrogen monoxide and 1 mole of oxygen. That's 3 moles on the reactant side, and on the product side we have 2 moles of nitrogen dioxide. So we're actually combining, this is a combination reaction, we're combining 3 moles and making 2 moles. So there's actually a decrease in the number of moles of gas. That means that there's probably more order to this system. Just so that you think of this and think about what our final number is. You want to have some concept of what the number should be in your mind before you do the calculation. So now what I'm going to do is very carefully pull out the values from that thermodynamic table here that is in the aqua blue color there and plug that in right there. So delta S naught for the system is equal to 2 moles of nitrogen dioxide times its value, which is 240.04 joules per Kelvin moles, minus 2 moles of nitrogen monoxide times its value of 210.76 joules per Kelvin mole, plus 1 mole of oxygen at 205.07 joules per Kelvin mole. Again, molecular oxygen does have a value for entropy values. I'm going to do my multiplication, then my addition. I'm using the fewest number of decimal places, which everything here has 2 decimal places, so my answer should have 2 decimal places. So delta S naught for the system is equal to negative 146.51 joules per Kelvin. Notice that the moles cancels out, but the joules per Kelvin stayed there. Okay, and then I'm going to ask myself, what does that negative sign mean? And I'm going to come back to that balanced equation here. So the negative sign indicates that there is a decrease in the entropy, i.e. there is more order on the product side than compared to the reactant side. That is characteristic of a combination reaction, by the way. Okay, and this is seen in the decrease in the total number of moles from 3 moles on the reactant side to 2 moles on the product side, both being gases. And I kind of aforementioned that already. Hopefully that makes sense for you. I am the crazy hat chemist, so of course I got a crazy hat. And oh yeah, this is a crazy hat. Check that hat out. Give me a thumbs up if you like that video. Please subscribe to my YouTube channel, and I would greatly appreciate you passing that on to all your cool chemistry colleagues and friends that need help in chemistry. Please donate to my website. You might get a sticker that my son designed, or maybe even donate and you get a t-shirt. Gotta love that. Spread the word, give me a thumbs up, subscribe to my YouTube channel, and I'm going to see you next time. Bye for now.